Hello students, welcome to 5th lecture of D and F block elements competitive. In previous lecture we discussed about copper and its compound, and in this lecture let's start with silver. So silver can be obtained from the ores like argentine, horn silver, ruby silver, etc. So extraction process is cyanide process or MacArthur's forest cyanide process. This method depends on the fact that silver, its sulfide or chloride forms soluble complex with alkali cyanide in silver. This implies that the silver compounds will dissolve in the solution of alkali cyanide in presence of blast of air. So reaction is mentioned when 4 silver and NaCN reacts in presence of water and oxygen. It forms NaAgCN2 and 4NaOH. And to be specific, we need cyanide ions in this case actually, and Na plus will behave as audience. That means it will present for neutralization purpose only. So our main product will be AgCN4 minus. This is water soluble compound, so we can filter it, and then our solution contains silver in it, and so we can reduce it again to get metal silver. Similarly, Ag2S with NaCN forms same type of compound, and AgCl again forms same type of compound. So that means we can get water soluble silver compounds using this method. Now the reaction with the sulfide is reversible, and the accumulation of Na2S must be prevented. A free access of air is continuously passed through the solution, which oxidizes Na2S into sulfate and thiosulfate. So metals of sodium or sodium sulfide, when reacts with oxygen and water, it forms Na2S2O3. That means we have sulfur here, Na2S, so it forms Na2S2O3. This Na2S2O3, when reacts with NaOH in presence of oxygen, it forms Na2SO4. That means thiosulfate and sulfate ions. And remaining reaction can be continued as follows. So we have NaAgCN2, that means complex compound of silver, and it can be reduced with zinc because zinc is comparatively more reactive than silver, and we can confirm it using their oxidation potential values. For silver, oxidation potential values is 0.8, whereas for zinc it is minus 0.76. So we have a lot difference between them, and higher the value of reduction potential, more will be the tendency of reduction, and lower value, that means more tendency of oxidation. So normal tendency of zinc is to get oxidized, and for silver it will be to reduce. That's why after the reaction you will get zinc compound and silver in metallic form. And metal silver, that means it is insoluble. So again just filter it and you will get solid metals pieces of silver. Now next, extraction of silver from argentiferous lead, which is known as Parkes process. It is based upon the following fact. First, molten zinc and lead are immiscible. Zinc forms the upper layer. That means just like water and oil will float above the water. Similarly, zinc will float above the lead, because leads are generally lead is one of the heavy metal or dense metal. That's why density of zinc is more, lead is more. That's why it will be at the bottom and zinc will float on it. Second, silver is more soluble in molten zinc. And third, zinc mercury alloy solidifies earlier than the molten lead. And fifth point, zinc being volatile can be separated from the silver by distillation, and silver is purified by cupellation. Now cupellation, that means heating the mixture with very high temperature, and by controlled operation we can separate out some noble metals like gold, silver, platinum, etc. Now properties: silver is a white lustrous metal, best conductor of heat and electricity. Being soft, it is alloyed. That means we will mix some other metals to increase the strength of silver. Now as mentioned, it is very good conductor of electricity. So that means we can use it in certain compounds or certain circuits in which we need very high conductance value. Usually copper is we can say that one of the second best option we have after the silver. It is a good conductor of electricity but not as good as silver. But silver is comparatively costlier, that's why we cannot use in our regular devices. So if specific requirements are necessary, then we will use silver, otherwise copper is being used. Now, silver alloy used for making jewelries contains 80% silver and 20% copper. Simple reason, to increase the strength, otherwise it will be very soft. So the composition of silver alloy is expressed as its purity, that is the amount of silver present in 1000 part of alloy. Ag does not react with dilute HCl or dilute H2SO4 because it is considered as noble metal, and usually noble word represents very less reactive or almost non-reactive, and it also do not react with aqua regia, but it reacts with dilute HNO3 and con HNO3, forming NO and NO2 respectively. The chlorine also react with silver to form AgCl, so widely we will use silver in form of AgCl in our laboratories or in form of AgNO3. Con H2SO4 reacts with silver forming SO2 like copper. Now compounds of copper. First, silver oxide. It is unstable and decomposes into silver and O2 on slow heating because it is noble. Noble, that means mostly it will try to remain in its metallic atomic state. So if we have compound and if you provide a little bit amount of energy, then it will start converting itself into atomic state, as we can see here. In this case, silver is in +1 oxidation state, but after the reaction it catches its electron from the oxygen and you will get silver metal. Silver halide, we have different type of examples. Almost all the halogens forms halides with silver. Out of all, AgF is the soluble in water, and AgCl is insoluble in water but dissolves in NH4OH, Na2S2O3 and KCN solutions. AgBr is partially soluble, whereas AgI is completely insoluble in NH4OH. Except AgF, all the remaining three silver halides are photosensitive. That means it can react in presence of light. If we apply the light on the surface of these given examples, then they will change their colors and chemical properties. So that's why these type of compounds were used in earlier photography development processes. Right now we use digital printers, so that's why we do not need these type of reactions anymore. Now reactions are mentioned. AgCl with NH4OH forms AgNH3 twice Cl diamine silver 1 chloride compound, which is complex compound. Similarly, AgCl with KCN forms potassium dicyanoargentate 1 compound. Now note here name of metal is mentioned as silver and here it is mentioned as argentate. Reason for that is when our complex compound is positive, then we will use normal name of metal, and as we can see here we have AgNH3 twice. If you check the oxidation state of each, then silver is in +1 oxidation state, ammonia will be neutral, so 2 ammonia total gives 0 oxidation state. That's why overall oxidation state of this complex will be +1. Whereas if we check this second example, then we have cyanide which has -1 oxidation state. Because of 2 you will get -2 oxidation state. Silver is in +1 oxidation state, so overall oxidation state of complex will be minus. That's why if complex is negative, then we have to attach at suffix after the name of metal. So silverate is not suitable name. That's why we will use the second name of silver, which is argentane, and we will fix at suffix after it. Okay, so symbol Ag is derived from the second name of the silver, argentate. Similarly, for gold it is also called aurum, and from the name aurum symbol Ou is derived. And similar situation will be observed in third example. Again we have negative complex, and that's why argentate is mentioned. So AgCl with Na2S2O3 gives Na3AgS2O3 twice, which is known as sodium disulfito argentate. Now next, silver nitrate, mainly used chemical in laboratory by us. Silver nitrate is called lunar caustic silver nitrate, and on heating above its melting point it decomposes to silver nitrite, but on heating to red heat it gives silver. So AgNO3 on heating above 485 Kelvin it gives AgNO3, and when we heat AgNO2, sorry, and when we heat AgNO3 at red hot heat temperature, then it gives silver metal. Now when treated with alkali, AgNO3 forms silver oxide, which in case of NH4OH dissolves to form complex ion. So AgNO3 with NOH it gives Ag2O. Now AgNO3 with NH4OH again forms Ag2O, and Ag2O with NH4OH, that means in excess amount, forms AgNH3 twice OH, diamine silver hydroxide. Now AgNO3 reacts with iodine in two different ways, so different quantities gives us different type of products. When we have AgNO3 in excess quantity, then our main product will be AgIO3 and AgI. Whereas when we have iodine in excess quantity, our products will be AgI, which is common, and second HiO3. In contact with organic matter, skin, cloth, paper, etc., AgNO3 is reduced to metallic silver, which is black in color. Okay, when it reacts directly with the skin, clothes, or paper, it gives black color. So we can use it as a black ink for certain materials. AgNO3 H2O, it gives Ag and HNO3, and O represents oxidizes organic matter. AgNO3 gives different colored PPT with different anions like Cl minus, Br minus, I minus, S minus 2, S2, O32 minus, CrO32 minus, and PO43 minus. Now this point is important because in our inorganic qualitative analysis we use AgNO3 to identify negative ions as mentioned here. It gives different colored precipitates with negative ions mentioned here. So it is our one of the test to identify negative ion in given inorganic compound. Okay, so this point should be noted and it should be remembered. AgNO3 is used in preparation of ink and hair dye. As mentioned in previous point, in contact with organic matter, it gives black color because it is reduced in metallic silver. And again, as mentioned earlier, it forms photosensitive material with halogens. So one of the use will be in photography. So photographic plate is coated with the colloidal gelatinous solution of silver bromide. During the exposure, silver bromide is reduced to metallic silver, and that's why, as mentioned again, it gives black color. So silver in metallic form gives black color. So different amount of light when we expose on the silver bromide solution layered on the surface, it gives different type of colors. So exposed film is developed. The developer used is alkaline solution of hydroquinone or quinol, which reduces some of the exposed silver bromide to black silver. So reaction will be quinol with silver bromide reduces silver into silver metal and quinone is obtained. And then the film is finally fixed by dipping in the solution of sodium thiosulfide or hypo, which removes uncharged AgBr as complex ion. So AgBr with Na2S2O3 gives Na3AgS2O3 twice, which is already discussed earlier. Now after taking the print of the photograph, it is finally toned by dipping in dilute solution of gold chloride to impart beautiful golden color, or it is dipped in potassium chloroplatinate K2PtCl6 solution to get a shiny gray tint. So AuCl3 plus 3Ag gives AgCl and Au. So again this reaction represents gold is more stable than the silver, or if we check the reduction potential of gold, then it will be even higher than the silver. So it represents gold has more tendency to reduce itself than the silver. So this last point, that means photography film, we do not use it anymore for regular photography. It was for earlier times when we use rolls in camera. And now we use digital cameras which do not require these type of methods. and we can directly print those photos via printers. Okay, so this was old photography method mentioned here.